simulate situations
The
in engineering.
concept and direction
Situations which we do.
Processing is about the immediacy
brings a world of
of expressing
information
an
about
idea. So
events far out
it's
at
the
sea.
quickest route for me from
What is time for? Time is what hinders everything from being given at once. It retards, or rather it is, retardation. It must therefore be elaboration. Would it not then be a vehicle of creation and of choice? Would not the existence of time probe that there is indetermination of things? Things are participants in a choreography, molecules in movement, furrows in the ground, servers and databases, swarms and herds, vehicles set in order, people in a chain, information, users in a social network, ocean currents, flocks of birds, life in motion, intelligent, synchronizing itself, interacting with each other, tidying itself up, pursuing itself, communicating itself, imitating itself. All of those are processes. Processes that need all participants to come to an agreement in order to operate, to share codes, recipes, or instructions.
D C
Rules and codes do not hinder the chance to create. They, being around us, are what cause the constant change. Finding codes allows us to build tools to interact with processes. We can come closer to the world's phenomena and simulate them. We can visualize the data shown in processes happening around us, or give rise to new creative processes, alive and open, available for reappropriation and expansion by everyone.
processing is a language and a toolkit and a community and an open source project. And I think I think of it as kind of a way of dealing with creativity and coding, but also it's kind of my model for what I think of an ideal online community. People who are supporting each other and learning similar things and helping people who are just starting and sharing ideas and things like that. So processing to me is all of those things.
Processing is a really excellent tool which allows people, just about anybody with any kind of background, to start working with code as a creative medium. So it's very easy to make animated sketches or drawings in code without necessarily having a lot of knowledge about Java or programming in a proper way.
So it's a digital sketchbook. It's somewhere where you can scribble down your ideas in code. But just like a sketchbook, those ideas might become real things. The difference between processing and a real sketchbook is that that sketch can become something bigger and more elaborate. It's as if your art sketchbook, your drawing sketchbook, could suddenly become a movie or could become a sculpture.
One of the great things about working with processing is that when you have an idea, it's a very short path to being able to see that idea become real.
For me, processing is about the immediacy of expressing an idea. So it's the quickest route for me from code to pixels on screen.
watch them turning and wheeling, how often have we wondered what holds such birds together in their flight? And though these people seem unaware of each other's existence, neither looking nor speaking, one group meets and filters through the other, with hardly two individuals coming in contact. So constant is the flow of information, and so complex the web of communication that keeps them apart and holds them together. A wave breaking on a beach brings a world of information about events far out at sea. It can tell of winds and storms, the distance and the intensity. It can locate reefs and islands and many things, if you know the code.
Code, essentially, when you explain it to people, okay, so what do you mean by code? Well, code is literally just the language that you have to describe your ideas in for the computer to be able to execute them. And the computer is a very stupid machine in many ways because it needs to have everything very clearly described. So in that sense, it's a language or a way of describing logic. And then you add different kind of parameters or different logics to it. Maybe you add in interfaces, etc. So the code can become very alive later. But in its basic form, it's like lines and lines of text, and it doesn't look very friendly or very human or very elegant at all. And sometimes code is very, very frustrating. But it also is. There is a certain elegance to being that precise.
When you write a computer program, you are basically encoding an idea into a specific notation that a computer can run. And those ideas, which oftentimes in software we call algorithms.
He must write a concise step-by-step list of instructions, translate it into a digestible code, and feed it to the computer.
The system calls for the key to be either up or down. The code calls for a dot or a dash. The current flows. It ceases to flow, it flows. It is black or white. It is stop or go. On or off. One or none. Go or no go. Or black or white.
What is the nature of this remarkable correspondence between the abstract symbols of mathematics and logic and the real perceptible world of objects and events? Mathematics has been called the one universal language of mankind. But what are these rules, and what is the relationship between numbers and the real things they are said to represent?
We rethink a little bit about the role of contemporary math, not just financial math, but math in general, that it's transitioned from being something that we sort of extract and derive from the world to something that actually starts to shape it. The world around us and the world inside us, and it's specifically algorithms, which are basically the math that computers use to decide stuff, right? You can find these kinds of things wherever you look once you learn how to look for them. And we will have to understand those as nature. And in a way, they are.
Okay, anyone that knows me knows I'm an algorithmic guy. I really like this process of describing operations to a computer and having that computer go through and step through these operations. So let's imagine in this system that we create a line. The line will continue to draw until it hits either the edge of the screen or another line. New lines will also only form at right angles to existing lines. So those are the rules, but if we repeat those processes over and over again, something kind of amazing happens. So I'm just going to let this go.
You might be wondering again, who are these people and what do they do? So sort of what we like to think that we're doing is if you think about nature as being driven by this universal tool set of processes, what we're trying to do at Nervous System is play with this tool set and see what can we make with it. And then here's a lamp growing. You can watch the process. And each lamp is unique.
So one of the things that we're trying to do is use the tools of science, but use them in a way that's not traditionally scientific. Because science is trying to replicate or describe reality, and it's always about quantitative results rather than qualitative results. We don't really care if the models that we're using make accurate predictions. We're working purely with qualitative aspects, so how systems can generate certain structures and how those structures can vary. So instead of trying to make something similar to reality, we're trying to make things that are distinctly unnatural but have sort of that natural organicism and feel.
So the work that I do is an attempt to try to fill myself and hopefully others with a sense of wonder for the things that surround us by trying to do simulations, which will hopefully help you think about things like this in a different way.
Bubble motion in microgravity. Here we have a flask filled with water and bubbles, and look at the motion of the bubbles. They tend to move around in a circle.
This is a simple gravitational experiment. I've just put a bunch of particles in a zero-G space, if you want to call it that. And so with 1,000 particles, each particle exerting a force on 999 other particles, you end up with about 1 million force calculations per frame. It was nice to finally be able to not have to tell the particles what to do. I just tell them that they need to react to each other, and they start to do some things which become really unexpected. When you're just applying Perlin noise to a bunch of particles, you're not going to get anything unexpected because there's nothing unexpected in that math. But when the particles are forced to interact with each other, the more particles you have, the more possibilities there are for these interactions, and you can come up with some really impressive and organic responses.
The computer can produce a new idea or make an original contribution to knowledge. We ask this question of both Professor Nagel and Dr. Hamming.
In some senses, the machine only produces what you expect. On the other hand, you do not foresee all combinations, and the machine often produces combinations which you had not foreseen and have the impression of novelty.
But once set up, it can attack the problem with infinite variations and trustworthy memory.
When we watch them turning and wheeling, how often have we wondered what holds such birds together in their flight?
One of the core ideas of processing is this idea of sketching with code. And so actually the files that you save in processing are called sketches. And the idea there is that instead of just imagining something, you can actually write a small piece of code and then experience it and then develop it from there. So for everything that I do and that many people who work with processing do is to make a lot of sketches by hand first as a way of like really quickly getting ideas and imagining what things can do. But then at some point you move over to this idea of sketching in code where you make small samples, small tests, small prototypes, and then you launch the program and sort of see how it's working. And then from there you make changes and modifications, and it's called like an iterative design approach or iterative methodology where you gradually you see it and evaluate it and then make changes from there.
That's in real contrast to the way that you typically think about writing computer programs, where it's this very methodical, like, well, I'll solve all the problems first in my head, and then I'll sit down and make the code that does that and just debug it. We want people to do is try something, write a little bit of code, see what happens, write a little bit more code and see what happens, and not feel quite so precious about the things that they make with code, and to be, have that same sort of comfort of when you're dealing with your sketchbook, being willing to flip to a new page or scribble something out or crumple it up and throw it away and never look at it again. And
this is information. The proper use of it can bring a new dignity to mankind. Properly related, it can maintain a balance between man's needs and his resources. In many aspects, these are information machines, capable of storing, processing, and relating a vast quantity of information. They process information so that it can be made meaningful at the human scale.
We have increasingly augmented our capacity for producing information, classifying it, collecting it, archiving it, and we are increasingly generating more and more of it, but we cannot increase with our traditional tools, with the same tools as ever, our capacities of comprehension and analysis.
Como é que você faz, como é que você entende todo esse mar de números, né? É muito bom a gente ter essas informações disponíveis para a gente online, mas a gente tem que ter algum tipo de tradutor para que a gente consiga lidar com essas informações numa escala humana.
And computation is a very important tool in terms of analyzing and also displaying data.
So it makes sense that if we're gonna need to face a much more level of complexity in our relationship with all the systems in our culture, we also need a new syntax, a new language. And data visualization is so far the best thing that we seem to have.
Desses tradutores que a gente pode usar é essa tecnologia chamada visualização de dados, que pega esse número, esse mar de números, né, e transforma, pinta uma imagem que te permite entender coisas como tendências, anomalias, o que é normal, o que é anormal nessas informações que você está olhando.
Idea about the ease of data, like the ease of access to data is very new, and the ease of access for the whole world to be able to make charts or graphs is relatively new, right? I think Excel really revolutionized that, but now other tools as well, like when you want to move into fancier stuff.
If people put data onto the web, government data, scientific data, community data, whatever it is, it will be used by other people to do wonderful things in ways that they never have imagined. There is an open data movement afoot now around the world. The cry of raw data now, which I made people make in the auditorium, was heard around the world.
Realmente, se a gente está numa revolução, a gente tem que ter consciência dessa revolução. Não adianta só você me encher de planilha, de números, se eu não sei ler essas planilhas e se eu não sei entender o que você está querendo me dizer com todos esses dados, né? Então, visualização é uma maneira da gente tentar começar a interagir com essa riqueza de informação.
Every weekday, for 12 years, Harold would brush each of his 32 teeth 76 times. 38 times back and forth, 38 times up and down.
One of my favorite artists is this guy, Nicholas Felton, who creates these things called the annual reports. I don't know if you're familiar with it, but he basically makes these annual reports of his life. He obsessively tracks every detail of how many beers he's had, what streets he's been on, and hand designs these beautiful booklets once a year in January every year that he publishes and sells, the Felton Report, I believe it's called. And he just recently started using, I met him in New York recently, and he recently started using processing because there are certain things, it's, for him, his work, I believe, is really about meticulous detail, and I'm sure he just loves tweaking little things in Illustrator and making it perfect, and he should be able to do that. But there's certain aspects of analyzing and looking at his data that one of the things he was showing me was this sort of diagram that it would have taken weeks to do in processing, by hand, and he could do it almost instantly in processing. But it's not just about saving time. There's certain things you can discover and create and be creative with through computation that you can't with by hand. They both go together.
I mean, I think it's really our ability to reveal some patterns or provide context, like in a visual or a visceral way, right? Like to be able to see structure. I think one of our, some of our most successful data visualizations are the ones that allow you to uncover some kind of relationships or structure or patterns that would be very difficult to describe in words or in a photograph. Right?
Let's see how they operate. First, input. Next, processing.
Electronic data processing.
This is the $1 billion-ogram, and this image arose
out of frustration I had with the reporting of billion-dollar amounts in the press. That is, they're meaningless without context. 500 billion for this pipeline, 20 billion for this war. It doesn't make any sense. So the only way to understand it is visually and relatively. So I scraped a load of reported figures from various news outlets and then scaled the boxes according to those amounts. And the colors here represent the motivation behind the money. So purple is fighting, and red is giving money away, and green is profiteering. And what you can see straight away is you start to have a different relationship to the numbers. You can literally see them.
To extend the range of human eyesight, man developed marvelously sensitive instruments.
As a function of design, the calculator provides creative man a higher platform upon which to stand and from which to work.
Our tools, these tools we're talking about, allow us to produce more insightful, more powerful, more broad-ranging visualizations simply by allowing the user to explore.
The more work that I do in that space, the more I'm finding that it's really even much less about how you ways in which you actually present the information than it is ways that you actually navigate through the information and interact with it.
A lot of the paradigms that we use for data visualization are still print paradigms, where you have a page that's static and you make your visualization and then you're done with it. The data visualization is about looking at data from different angles, and that allows people to look at the data in a way that they hadn't been able to look at it before. Go through this big jumble of events and stitch them together into these cascades, and then view these cascades and maybe find some insight about how people are sharing Times content and how people share content in general.
For a long time in the world of numbers, man has been developing tools to help him handle increasing amounts of data. Something has now emerged that might make even our most elegant theories work. A tool which has broadened the range of man's concepts and intuition, much the way other tools have broadened man's. With the computer, as with any tool, the concept and direction must come from the man. The task that is set and the data that is given must be man's decision and his responsibility.
One of the most important advantages of processing is that it makes it really easy to teach programming to people that are primarily interested in visual design and the arts. Processing makes it a lot simpler to write programs that put things on the screen faster.
The process of learning processing usually involved drawing a line on the screen. That was the first step. Draw a line from point A to point B. And so right away you've got, you're looking at a simple but a piece of art that you've made.
You learn to program computers by drawing. You learn to program computers by loading in images and doing things with those. You learn to program by making animation and interaction, visual experiences. So it's a way of basically bringing what we think is really thrilling and exciting about software into the visual arts at a level where people who are visually motivated and focused can explore, experiment, and play with code as a new way of realizing ideas.
And in particular, people who think visually, designers or artists or people who are used to thinking in terms of images or in terms of structure or form or aesthetics, they suddenly can work with processing, and processing already is oriented towards that kind of work. And it's more about supporting their activities as creatives than it is about having a perfect code, if you will. So compared to other programming languages, processing is much more directly prepared for people who might not be the greatest technicians, but who have good creative ideas.
Returning to our more general remarks about the use of computers, we first use computers to simulate situations in engineering, situations which we had been doing before by hand. The computers allowed us to do much larger and more complex problems. But this ignored the order of magnitude effect which we spoke of. We are now beginning to use the machines in entirely new ways on entirely different problems. And this is the exciting part. This is the intellectual aspect of applying the machines to completely new ideas that has so excited many people in the field.
I've energized a relay here, and this is the bank of amplifiers that drive the servo motors of the system.
The computer which created the Stargate corridor in the film 2001 was developed by the man behind these glasses, John Whitney. His 3 sons and his brother James have all used his machines to make computer films. The Whitneys are not inhibited by the specter of giant computer companies.
Hardly to be called computers because they're really specialized problem solvers. They were computers that were designed to compute only on one kind of an equation.
And what I've been doing over the last decade or so is designing the simplest mechanisms that I can imagine. Very, very simple, primitive machines. And through using emergence, these machines, when they interact together in a basic environment, are able to produce things that are far more complex than their basic parts.
This is element 1. This is behavior 1. Behavior 2, behavior 3, behavior 4. This is element 1. An element is a simple machine that is comprised of a form and one or more behaviors. This diagram shows element 1 in action. The behavior is easier to see when we add notation. These arrows show behavior 1, move in a straight line. These arrows show behavior 2, change direction while touching another. And these directions show behavior 3, move away from an overlapping element. A process defines an environment for elements and determines how the relationships between the elements are seen. Process 4 fills the surface with element 1 and draws a line between the elements while they overlap.
Computers will invade the arts, just as they do every other part of our lives. In the future, artists may have to learn new skills of mathematics, mechanics, engineering, and programming in order to practice their craft.
When you want to create a certain type of form or image in the computer, you need to be able to describe all the steps that go into making that image. And to do that, you create what is called an algorithm. And an algorithm is just like a recipe. You know, like if you're cooking a specific dinner, you need to have the recipe and the order in which you cook things, etc. It's the same thing in the computer. You need to say, okay, this form is created by having a particle that moves around, and the particle is controlled by rotation, and maybe sometimes it divides and becomes 2 particles. So that's an algorithm that's actually describing the entire behavior of the system. And so the algorithm is actually very much describes your creative idea.
Whenever you define a system in software, it's a limitless field that you can explore. And by changing different parameters, the value of different parts of the system, you move to different parts in that infinite landscape.
It's very clearly about manipulating algorithms and choosing parameters and figuring out how can I actually tease the beauty out of the system when the raw data in itself isn't very meaningful. So the potential is there in computational creativity to have processes that are very much non-human, and I think we often do see that, but we found sort of a middle ground joining the non-human, computer, strange, emergent processes, etc., with a human way of thinking about the world. And somewhere there's a very fruitful area.
I would like to tell you another anecdote from that 65 February Georg Ness exhibition. The leading fine artist, the painter Heinz Dröke, raised his hand and said, "Young man," addressing Georg Ness, "all said very well what you told us, but you know what? Could you make your machine draw the way I draw?" And Ness pondered for a moment, and they said, "You know what? If you tell me how you draw, I can make my machine do it. So what is nice about this anecdote in a nutshell is that both were right. Trökes, of course, with his assumption that the answer would be no, because how could a machine draw like he did? But Georg Nees was right also when he says, if you can tell me how you draw, I can make my machine draw. Because, of course, you can, if you draw as an artist, you cannot tell how you do that. You do it and it happens. So there we had, at the very moment when algorithmic art started, a little story that clearly shows the difference, that then through the next few years only, everything that concerns algorithmic art happened.
So when I'm doing this work, a lot of what I'm trying to do is to create these very ambiguous environments where they're not intended to represent anything. They're not intended to have any narrative behind them, but they're intended to be spaces that invite questions and invite curiosity. Sort of a dialogue around wondering what it is and how it works is the intent.
The essential quality of digital data is that it's plastic. It's capable of changing, state, assuming ever-changing configurations on demand, and it's capable of sort of universal representation of other media, if you will.
Thus, the man-machine combination will find a dividing line passing gradually from man over to machine, machine taking more and more of the burden as we learn how to use the machines, and as the machines become more powerful, and we will find ourselves left in the more creative aspects of the problem.
Don't see, for instance, shapes or objects we design, or even tools are objects. We don't see them as those static items anymore we simply use, but we actually start inquiring what are the underlying processes, and how, once we understand those processes, what is the design potential to manipulate them and then really create truly new solutions which weren't even possible beforehand.
So James Surowiecki has this idea of the wisdom of crowds, which says that a whole bunch of people are smarter than any individual. We want to see how this applies to collaborative distributed music making, where nobody has any idea what it is they're working on. The song Daisy Bell, which was the world's first singing computer. So we resynthesized this song. This is kind of what that sounded like. We broke down all the individual notes in the singing, as well as the phonemes in the singing. And we took all those individual pieces and we fed them into another Turk request. This is what it would look like if you went to the site. You type in your code. You first test your mic.
Hello.
You'd be fed a simple audio clip. Then you do your best to recreate that with your own voice.
Community's been, I think, really the foundation of the entire project. And when we were developing and designing the software, we were always doing it in relationship to teaching with it and to the community. So really early on, we basically employed really basic social media tools, like at that time a bulletin board and email lists and all those kinds of things. But as we developed the software, we were always releasing it, getting feedback, and incorporating that into the piece.
I think actually the best way to get started is the way that the project itself got started. So find somebody who's giving a workshop or giving a tutorial who's willing to help you through those first steps and give you the confidence that you know, this is what coding is, this is what design and code look like when they're done at the same time together.
At the very beginning, one of the most important things about processing was that people would be able to take what they've made and to put it online so other people could see it.
For me, something that has been very useful in helping me grow as a programmer is to look at other people's source code.
You don't have to reinvent the wheel. You can take that and you can say, okay, well, this is useful to me. Now I want to look at it a different way and put some different code around this.
And so the idea that you can make something in processing, export it into a way that you can just immediately put it on the web, and the source code's included in there, has been really essential for the project.
I mean, there are hundreds of thousands of people who use processing. So if that's the community, then it's very large. If you talk about people who are actively using processing and would wear the T-shirt, then maybe it's in the order of several thousand.
Later on, the community really, in a way, became the major part of the project through this system of libraries that we put in. So processing by design is meant to be a core, pretty minimal framework, and then we built in a way that people can extend the software through writing these libraries.
When I come up with something that I realize that most people don't know how to do, or someone just hasn't done it yet, I will make it available to other people. So for instance, with the MakerBot project, I released both the models that I had made as totally open source, which of course as an artist you would normally not do. You're not going to just put your artwork out in the world for anybody to make, but also the code, which is much more important because the code is actually the tool that you use to create the thing.
So I think the idea that processing is just for doing graphics on screen has really evolved a lot in the years, and through prototyping and then fabrication, its use has been really extended into a lot of different domains. And the core of this work is really with the libraries. So processing now has over 100 contributed libraries, and this is really how the project stays dynamic and evolves very quickly. Our strategy is to keep the core and the base of processing very minimal and contained, and to then make this system that allow other people to contribute projects.
I couldn't do what I do without open source. I really believe in this, we all are standing on the shoulders of giants, and I really feel it's important to give back what you take.
The universe endures. The more we study the nature of time, the more we comprehend that duration means invention, the creation of forms, the continual elaboration of the absolutely new. For instance, this documentary, it is made up of many found documents. In turn, those documents are the result of previous developments. They are open documents, which can give rise to other processes. The process of assembling different documents causes unexpected results. All processes are part of the universe, and they need agents, codes, and time to operate. Manipulating codes permits a closer approach to processes. It permits you to look at data from the distance and with perspective, or to create new and unheard processes. To do this, to create these kinds of tools, is why we need languages like processing.
But finally, the future, except in terms of trends and probabilities, is the great unknown. And the uses to which we put ourselves in relation to the marvelous machines of our own invention is perhaps the central moral and intellectual challenge of our own brief moment in time.